the universe should not exist. According to the strictest equations ever written, everything should have cancelled itself out in the first moments after the Big Bang. Matter and antimatter should have been created in perfectly equal amounts, mirror images born together from pure energy, and when those mirrors met, they should have annihilated entirely. No stars, no planets, no galaxies, no time for chemistry or life. Just a fading glow of light spreading through an empty cosmos. And yet, here, everything is. Solid, heavy, stable. A universe built almost entirely from matter, with antimatter reduced to a rare laboratory curiosity. This imbalance is not a small mystery or a missing decimal place. It is a fundamental contradiction between what the universe does and what the laws of physics say it should do. For decades, this contradiction has been one of the most uncomfortable problems in science, a quiet embarrassment hidden behind equations that otherwise work with astonishing precision. And now, deep underground at CERN, in facilities far removed from the famous particle collisions, scientists have been studying antimatter not by smashing it, but by trapping it, cooling it, holding it still, and watching how it behaves when nothing else is interfering. What they are finding is subtle, difficult to measure, and impossible to ignore. Antimatter is behaving exactly as it should in many ways, but the deeper it is examined, the more it raises a dangerous question. Not whether antimatter is strange, but whether the rules governing matter itself are incomplete. This story is not about explosions or science fiction fuel. It is about precision, patience, and a universe that appears to have survived its own creation by the smallest possible margin. In the early moments of the universe, when everything was compressed into a state hotter and denser than the core of any star, energy itself began to condense into particles. This process was not selective or creative in any artistic sense. It followed strict accounting rules. Every particle of matter had to be accompanied by an antiparticle with the same mass and opposite charge. Protons were paired with antiprotons, electrons with positrons. The universe, at birth, should have been perfectly symmetrical. A flawless mirror. In that environment, collisions were unavoidable. Matter and antimatter met constantly, and when they met, they annihilated, converting their entire mass into pure energy with absolute efficiency. Creation and destruction happened side by side, faster than time itself could meaningfully pass. For a brief instant, the universe was a seething equilibrium, a churning sea where nothing could settle or survive. According to theory, this balance should have continued until expansion cooled the cosmos just enough for the annihilations to end. And when they ended, there should have been nothing left behind. Just radiation, drifting forever. But that is not what happened. Somewhere in that chaos, the balance tipped. Not dramatically, not violently, but by an amount so small it almost feels insulting to the grandeur of the universe. For roughly every billion pairs of matter and antimatter that destroyed each other, there was one extra particle of matter left over. One. That single survivor, multiplied across the entire universe, became everything that exists today. Every atom in every star, every molecule in every living cell, every grain of dust between galaxies traces its existence back to that infinitesimal surplus. The universe did not win a decisive victory. It survived by a rounding error. As the universe expanded and cooled, the frantic creation and destruction slowed. Space stretched. Temperatures fell. The constant collisions that had once erased matter as quickly as it formed began to thin out. This should have been the moment when everything disappeared completely, the final balancing of the cosmic books. Instead, a tiny residue remained. That leftover matter did not dominate because it was stronger or more stable. It dominated simply because it was there. With nothing left to annihilate it, it endured. Those surviving particles clumped together under gravity, forming the first simple nuclei, then atoms, then clouds of gas that collapsed into the earliest stars. Every structure that followed is a consequence of that initial imbalance, frozen into the universe before it was even a second old. For decades, physicists hoped the explanation would be simple. Perhaps antimatter was hiding somewhere far beyond our reach. Perhaps entire galaxies were made of it, separated from us by vast distances. But the universe does not keep secrets quietly. If regions of matter and antimatter existed side by side, their boundaries would glow with unmistakable signatures of annihilation, releasing high energy, radiation visible across cosmic distances. Astronomers searched for those signals and found none. The observable universe is overwhelmingly uniform. Everywhere we look, the same matter dominates. Antimatter is not hiding in the dark. It is missing. This absence turned antimatter into more than a curiosity. It became a diagnostic tool. If the universe once treated matter and antimatter differently, that difference must still exist somewhere in the laws of physics. It must be encoded in how particles behave, how they decay, how they respond to forces. The problem is that these differences, if they exist at all, are incredibly small. They are drowned out by noise, masked by stronger interactions, and invisible in violent collisions. To see them, scientists had to change strategy. Instead of smashing particles together at enormous energies, they began slowing them down, pooling them, isolating them from the chaos, watching antimatter in near-perfect stillness, where even the faintest deviation from symmetry could no longer hide. That shift in approach led away from the most famous machines at CERN and toward quieter halls deep underground, where antimatter is not destroyed on contact, but suspended in carefully balanced magnetic fields. Here, antiprotons are slowed from near light speed to a crawl. Positrons are cooled to temperatures colder than the space between galaxies. Antiatoms are assembled one at a time and held in place long enough to be studied, sometimes for minutes at a time. These experiments are not spectacular in the traditional sense. There are no giant collisions or showers of debris. But what they offer instead is something far more dangerous to existing theory. They offer clarity. When antimatter is finally held still, stripped of excuses and environmental interference, it can be asked the most basic questions imaginable. Does it weigh the same as matter? Does it fall the same way in a gravitational field? Does it emit light at the same frequencies? Does it obey the same internal rules, or does it carry a faint scar from the moment the universe chose sides? These questions sound simple, almost childish, but they strike at the core of modern physics. Because if antimatter answers even one of them differently, the implications ripple outward, touching cosmology, quantum theory, and the origin of existence itself. This is where the story truly begins. Not with destruction, but with restraint. Not with violence, but with precision. In trying to understand why anything exists at all, physicists have been forced to confront the possibility that the universe is not as symmetrical as it appears. But somewhere deep in its foundation, there is a preference, a bias, a rule written so subtly that it only reveals itself when antimatter is treated with extraordinary care. And inside the antimatter experiments at CERN, that rule is being tested with a patience that borders on obsession. As antimatter became something that could be held rather than instantly destroyed, a new kind of investigation began. Instead of asking what antimatter does when it is smashed apart, scientists began asking how it behaves when left alone. This distinction matters because violence hides detail. High-energy collisions are excellent for discovering new particles, but they are terrible for detecting subtle differences. Any small asymmetry is buried beneath chaos. To uncover whether matter and antimatter truly follow identical rules, they must be studied in the calmest conditions imaginable, stripped down to their simplest possible states. Antimatter, however, resists calm by its very nature. The moment it touches ordinary matter, it annihilates. This makes even basic handling an engineering nightmare. Antiprotons cannot be stored in containers, and antiatoms cannot rest on surfaces. The only way to keep them alive is to suspend them in emptiness, using magnetic fields to hold charged particles away from the walls of a vacuum chamber. These traps are delicate systems balanced against forces billions of times stronger than gravity. A single stray atom of air, a tiny fluctuation in the field, or a momentary loss of power is enough to end the experiment instantly. Precision is not optional. It is survival. Once trapped, antimatter becomes an unusually honest witness. It does not carry the complexity of composite matter systems or the noise of high-energy interactions. An atom of antihydrogen, consisting of a single antiproton orbited by a positron, is as simple as nature allows. It mirrors the most abundant atom in the universe, hydrogen, but inverted. If any hidden difference exists between matter and antimatter, this is where it should reveal itself. Not dramatically, but quietly, in frequencies that shift by fractions of a fraction, or in motions that deviate by amounts smaller than intuition can grasp. One of the first questions scientists asked once antihydrogen could be reliably trapped was deceptively basic. Does antimatter respond to gravity in the same way as matter? Gravity is the weakest of the known forces, yet it governs the structure of the universe on the largest scales. According to Einstein's theory of general relativity, gravity does not care what something is made of. Everything with mass should fall in the same way. If antimatter were to behave differently, even slightly, it would signal a fundamental flaw in one of the most successful theories ever constructed. It would also offer a possible explanation for why matter and antimatter separated in the early universe instead of annihilating completely. Measuring this turned out to be far harder than it sounds. Gravity is so weak that even the tiniest electric or magnetic disturbance overwhelms it. Charged particles are useless for such tests, because stray fields dominate their motion. This is why neutral antihydrogen became essential. Only neutral atoms can fall freely enough for gravity to matter at all. At CERN, antihydrogen atoms were trapped in vertical magnetic fields, then carefully released while detectors watched where they struck the walls. The results showed that antimatter falls downward, just as matter does. There was no dramatic reversal, no anti-gravity effect. But the measurement was not perfect. The uncertainty was large enough that small deviations remained possible. Gravity did not solve the mystery. It narrowed it. With gravity offering no obvious escape, attention returned to symmetry. Physics is built on the assumption that the laws of nature do not change when certain transformations are applied. Swap left and right. Replace particles with antiparticles. Reverse the direction of time. In most situations, the equations remain unchanged. These symmetries are not philosophical preferences. They are mathematical requirements that underpin conservation laws and predictability itself. If they fail, the structure of physics begins to unravel. It has long been known that some of these symmetries are imperfect. Certain subatomic processes distinguish left from right, violating spatial symmetry. Others treat matter and antimatter differently under specific conditions, violating charge symmetry. These violations are real and measurable, but they are tiny. Crucially, they are far too small to explain why an entire universe ended up dominated by matter. The imbalance they produce is orders of magnitude weaker, than what cosmology demands. The equations account for cracks in the mirror, but not for the mirror shattering. This is why antimatter experiments at CERN are so unsettling. Every new measurement confirms the existing theories with increasing precision, yet the central problem remains untouched. Antimatter behaves almost exactly as expected. Its spectra match. Its mass matches. Its response to gravity matches within current limits. And yet, the universe itself stands as evidence that something, somewhere, does not match. The contradiction is not going away. It is becoming sharper. To resolve this, physicists are pushing antimatter tests into regimes where even the standard model begins to feel strained. They are comparing the magnetic properties of protons and antiprotons to extraordinary accuracy. They are measuring the internal energy levels of antihydrogen using laser spectroscopy, searching for shifts so small they would once have been dismissed as noise. They are treating antimatter not as an exotic curiosity, but as a precision instrument capable of exposing imperfections in reality itself. What makes this moment unusual is not that anomalies have been found, but that they have not. Each successful confirmation deepens the mystery. The tools are becoming powerful enough to reveal differences if they exist, yet the differences remain elusive. It raises an uncomfortable possibility. Either the mechanism that created the matter-dominated universe lies far beyond the reach of current experiments, or it is hidden in a place physicists are not yet looking. The antimatter trapped at CERN is not providing easy answers. It is providing a sharper question. How can a universe that should have erased itself obey the rules so perfectly and still exist at all? As the precision of these measurements improves, the focus shifts from dramatic violations to microscopic ones. The hope is no longer to find a single experiment that overturns physics overnight, but to locate a persistent deviation that refuses to disappear as the error bars shrink. In this regime, even a difference of 1 part in a billion matters. Such a discrepancy would not announce itself loudly. It would appear as a slight mismatch between expectation and reality, repeated across experiments, stubbornly resistant to explanation. This is how fundamental change usually enters physics, not as a shock, but as an irritation. One of the most powerful tools in this search is spectroscopy. Atoms absorb and emit light at very specific frequencies determined by their internal structure. Hydrogen has been studied so thoroughly that its spectral lines are among the most precisely measured quantities in all of science. If antihydrogen differs from hydrogen in even the smallest way, the frequencies of its emitted light will betray that difference. At CERN, lasers are tuned with extraordinary care and aimed at trapped antiatoms, coaxing them to transition between energy states. Detectors record the resulting photons and compare them directly with hydrogen's signature. So far, the match has been uncanny. The spectra align almost perfectly, as if nature is determined to preserve symmetry right down to the smallest detail. But this apparent perfection only deepens the puzzle. Cosmology demands that symmetry must have been broken violently in the early universe. The known sources of asymmetry are real, but too weak. Something else must have acted during those first fractions of a second, amplifying a tiny imbalance into the matter-dominated cosmos observed today. The challenge is that whatever caused this may no longer exist in an accessible form. It may have vanished as the universe cooled, leaving behind only its consequences. If that is the case, then modern experiments are searching for a fossil, a faint imprint frozen into the properties of particles themselves. This possibility has driven interest toward the most fundamental symmetries of all. While individual symmetries such as charge or parity can be violated without catastrophe, their combined form holds a special status. The combined transformation of charge, parity, and time is expected to leave the laws of physics unchanged under all normal conditions. This principle is so deeply embedded in modern theory that breaking it would force a reconsideration of causality itself. And yet, if the universe truly favors matter over antimatter at a fundamental level, then even this symmetry cannot be taken for granted. The only way to test it is through relentless comparison, measuring matter and antimatter with the same instruments under the same conditions, and looking for the smallest chapia, possible disagreement. Antiprotons have become particularly valuable in this regard. Unlike composite systems, they are elementary probes of symmetry. Their magnetic moments, masses, and charge-to-mass ratios can be measured with extraordinary precision in electromagnetic traps. By comparing these values directly to those of protons, scientists can test whether the mirror between matter and antimatter is perfectly aligned. Each new decimal place of agreement strengthens existing theory, but it also tightens the noose around alternative explanations. The more perfect the symmetry appears, the harder it becomes to explain why the universe ever diverged from it. At the same time, researchers are pushing antimatter into environments that were previously inaccessible. Portable traps are being developed to move antiprotons out of their production sites and into experiments designed for other purposes. This mobility changes antimatter from a static subject of study into an active probe. By introducing antiprotons into exotic nuclei, scientists can explore regions of nuclear structure that are otherwise hidden. These interactions are violent on microscopic scales, but controlled, producing data that reveal how matter behaves under extreme imbalance. In doing so, they may uncover clues about forces that operate differently in unstable systems, where symmetry is already strained. What makes these efforts remarkable is their patience. There is no guarantee that antimatter will reveal the missing asymmetry directly. The process resembles mapping a coastline in heavy fog, advancing meter by meter, marking where land should be, but is not. Each confirmed symmetry removes a possible explanation, narrowing the field of candidates. This slow elimination is frustrating, but it is also how physics progresses when confronted with a problem that refuses to yield to intuition. Meanwhile, theorists are forced to consider increasingly uncomfortable ideas. One possibility is that the asymmetry responsible for the universe's survival is tied to particles or forces that have yet to be observed. These hypothetical additions to physics could interact weakly with known matter, making them difficult to detect. Another possibility is that the asymmetry emerged from the vacuum itself, through fluctuations in fields that no longer exist in the same form. In this view, antimatter experiments are not expected to find dramatic violations, but subtle deviations that hint at deeper layers of structure beneath known laws. There is also the unsettling notion that the explanation may not lie in particle properties at all. The early universe was a rapidly changing environment, far from equilibrium, dominated by expansion and cooling on unimaginable scales. Under such conditions, processes that are forbidden or irrelevant today could have played a decisive role. If so, antimatter's present-day behavior may be an incomplete record, preserving only faint echoes of an event that reshaped reality before stable matter even had time to form. What keeps this investigation alive is the fact that the universe itself remains the ultimate anomaly. Every experiment confirming symmetry makes the existence of galaxies, stars, and atoms harder to explain, not easier. The laws of physics appear exquisitely balanced, yet the outcome they produced is profoundly unbalanced. Antimatter, studied with unprecedented care, continues to obey those laws while simultaneously highlighting their insufficiency. It is both compliant and accusatory, a perfect mirror that reflects a universe that should not have survived its own beginning. This tension defines the current state of antimatter research. There is no single discovery to point to, no dramatic announcement that resolves the paradox. Instead, there is a growing recognition that the solution will emerge only when precision becomes so extreme that even the smallest deviation cannot hide. Whether that deviation appears in antimatter's mass, its response to gravity, its internal structure, or its interaction with unknown forces remains uncertain. What is certain is that as long as matter exists at all, antimatter will remain one of the most important witnesses to the universe's earliest and most consequential mistake. As experiments continue to close in on ever smaller scales, the uncomfortable truth becomes harder to avoid. Antimatter keeps passing its tests. Each new comparison, each refined measurement, each reduction in uncertainty reinforces the same conclusion. Within the limits of what can currently be measured, antimatter behaves exactly as the equations say it should. And yet, those same equations fail catastrophically when asked to explain why anything exists at all. This disconnect has forced physicists into a strange intellectual corner, where success in the laboratory feels like failure on a cosmic scale. To understand why this is so troubling, it helps to revisit the idea of symmetry not as a philosophical preference, but as a structural necessity. Symmetries in physics are not decorative. They enforce conservation laws. They ensure stability. They allow cause and effect to function in an orderly way. When a symmetry is broken, it usually happens for a reason, and that reason leaves traces. Parity violation left unmistakable fingerprints in weak interactions. Charge and parity violation revealed themselves in the decays of strange particles. These discoveries were shocking, but they came with data that could be pointed to, quantified, and built into theory. The matter-antimatter imbalance, by contrast, is a symmetry-breaking event without a clear culprit. This has led some researchers to suspect that the imbalance did not arise from a single dramatic violation, but from a cumulative effect spread across many subtle processes. Instead of one large crack in the mirror, there may be millions of microscopic ones, each too small to notice on its own, but together sufficient to tip the balance. If that is the case, antimatter experiments must become even more refined, capable of detecting patterns rather than anomalies. The search becomes statistical rather than spectacular, a slow accumulation of evidence that something, somewhere, is consistently leaning in one direction. One promising avenue involves comparing how matter and antimatter interact with magnetic fields. Magnetic moments arise from the internal structure and motion of charged particles. They are exquisitely sensitive to underlying physics. By trapping single protons and antiprotons and measuring their magnetic behavior over long periods, scientists can test symmetry with extraordinary precision. These measurements demand extreme stability. Vibrations from nearby equipment, fluctuations in temperature, even distant seismic activity must be accounted for. When differences are sought at the level of parts per billion, nothing can be ignored. So far, these comparisons have revealed no meaningful discrepancy. Protons and antiprotons appear to be perfect opposites, matching each other's properties with unnerving fidelity. The mirror remains intact. Each time this happens, another potential explanation for the universe's asymmetry quietly disappears. It is a process of elimination that feels relentless. Physics is being boxed into fewer and fewer corners, and none of them are comfortable. At the same time, attention has turned towards systems that are inherently unstable. Stable particles are conservative. They resist change. Unstable particles, by contrast, reveal their inner workings through decay. The way a particle falls apart exposes the forces acting within it, and those forces may carry asymmetries that are otherwise hidden. This is why experiments at high-energy colliders continue to matter, even as low-energy antimatter studies gain prominence. The two approaches are complementary, probing different aspects of the same underlying mystery. Decays involving heavy particles are especially valuable because they offer more pathways. More pathways mean more opportunities for interference, and interference is where asymmetry can hide. In these complex decays, quantum effects can amplify tiny differences, making them detectable. Over the years, such studies have confirmed known sources of asymmetry, but again, the scale falls short. The imbalance produced is real, but insufficient. It explains curiosities, not universes. This persistent shortfall has led to speculation about physics beyond the Standard Model. The Standard Model is an extraordinary achievement, but it was never intended to be complete. It does not incorporate gravity. It does not account for dark matter. It does not explain dark energy. The matter-antimatter problem fits neatly into this list of omissions. It is a reminder that the theory, for all its precision, is a partial description of reality. Antimatter experiments at CERN are, in effect, stress tests, pushing the model to its limits and waiting for it to fail. One possibility is the existence of additional particles that played a role in the early universe and then vanished. These particles could have mediated interactions that favored matter over antimatter, leaving behind no direct trace other than the imbalance itself. If they existed only at extremely high energies or for extremely short times, recreating their effects today may be impossible. In this scenario, antimatter experiments are not expected to reveal dramatic violations, but they remain essential for ruling out alternatives and constraining theory. Another possibility involves the structure of the vacuum. In everyday language, a vacuum is empty. In quantum physics, it is anything but. Fields permeate space, and their fluctuations can influence particle behaviour in subtle ways. If the vacuum itself underwent a transition in the early universe, changing its properties as the cosmos cooled, it could have biased reactions involving matter, antimatter. Such a process would not necessarily leave an obvious imprint on individual particles today. It would have shaped the overall outcome without permanently altering the rules that now govern interactions. This idea is difficult to test directly, but it motivates experiments that probe how antimatter behaves in extreme isolation. By removing as many external influences as possible, scientists hope to detect deviations that cannot be explained by known interactions. These experiments are painstaking and slow, but they are driven by the recognition that the answer, if it exists, is not going to announce itself with fireworks. There is also the possibility that the universe is fundamentally probabilistic on the largest scales. In this view, the matter-antimatter imbalance is not the result of a deterministic law, but of a chance fluctuation amplified by cosmic expansion. Once the imbalance reached a critical threshold, it became locked in, preserved by the cooling universe. This explanation is deeply unsatisfying to many physicists because it offers no deeper mechanism, no reason beyond statistics. Yet it cannot be dismissed outright. Nature has shown a willingness to defy aesthetic expectations before. What keeps antimatter at the center of this debate is its role as a control case. Matter dominates the universe, but antimatter provides the comparison needed to identify bias. Without antimatter, there would be no way to tell whether the laws of physics are fair or skewed. By studying antimatter with increasing care, physicists are effectively interrogating the universe about its own history. Each measurement is a question asked of reality itself. Were the rules always this way? Or did they change when no one was watching? As the experiments grow more refined, the stakes grow higher. A confirmed deviation, no matter how small, would have profound implications. It could point toward new forces, new particles, or new principles that reshape our understanding of the cosmos. Conversely, continued agreement between matter and antimatter pushes physics toward more radical ideas about the origin of the imbalance. Either outcome forces a reckoning. The universe cannot remain both symmetrical in its laws and asymmetrical in its existence without explanation. For now, antimatter remains suspended in magnetic traps, isolated from the world it mirrors so perfectly. It does not explode. It does not rebel. It behaves. And in doing so, it quietly challenges the assumption that obedience implies understanding. The experiments at CERN are not searching for chaos. They are searching for the smallest possible failure of perfection. Somewhere within that failure, however subtle, lies the reason the universe did not erase itself at birth. As the search continues, the narrative begins to narrow. Not because answers are appearing, but because possibilities are disappearing. In science, this is often how progress feels from the inside. Doors close one by one, and the remaining corridors grow darker and more uncomfortable. Antimatter experiments have now eliminated entire classes of explanations that once seemed plausible. Gravity does not obviously repel antimatter. Basic properties such as mass and charge align with astonishing precision. Spectral fingerprints overlap almost perfectly. If there is a preference built into the universe, it is hiding extraordinarily well. This has forced physicists to examine the conditions of the early universe with renewed seriousness. The first moments after the Big Bang were not merely hot and dense, they were unstable in a way that has no modern analogue. Temperatures were so high that the forces of nature behaved differently. The distinctions between electromagnetic and weak interactions blurred. Particles that cannot exist today may have dominated the energy budget of the cosmos. In that environment, reactions could proceed along pathways that are now forbidden or irrelevant. The matter-antimatter imbalance may have been created during this brief window, then frozen in as the universe cooled and expanded. If this is correct, then modern antimatter behaves so obediently because it is no longer subject to the conditions that created the asymmetry. The crime scene has been erased. The culprit left no fingerprints. All that remains is the outcome. This idea explains why current experiments struggle to find dramatic violations. They are probing a universe that has already settled into a stable configuration long after the decisive events took place. The laws now appear symmetrical because the asymmetry has already done its work. Yet this explanation is not entirely satisfying. Physics has a long history of discovering that even ancient events leave subtle traces behind. Cosmic background radiation carries information about conditions hundreds of thousands of years after the Big Bang. The distribution of galaxies encodes the influence of primordial fluctuations. It is reasonable to expect that whatever tipped the balance between matter and antimatter also left some faint imprint on particle behavior. The challenge is to identify where that imprint might hide. This is why attention keeps returning to antimatter as a probe rather than a puzzle in itself. Antimatter is not important because it is exotic. It is important because it provides a controlled inversion of everything familiar. By flipping charge, comparing spectra, and testing responses under identical conditions, scientists can isolate effects that would otherwise be invisible. Antimatter experiments function like a subtraction, removing what is common to both and highlighting what remains. One emerging strategy is to combine antimatter studies with extreme precision timing. Time symmetry is as fundamental as spatial symmetry, yet it is rarely tested directly. In principle, the laws of physics should look the same whether processes run forward or backward in time, provided all charges and orientations are also reversed. This combined symmetry is deeply embedded in modern theory. If it fails, the consequences are severe. It would imply that the universe distinguishes past from future at a fundamental level, not just statistically. Testing this symmetry is extraordinarily difficult. It requires comparing the evolution of matter and antimatter systems over time with almost absurd accuracy. Any difference must be separated from environmental noise, instrumental drift, and statistical fluctuation. These experiments push technology to its limits. They are slow, repetitive, and unforgiving. But they address one of the last remaining pillars that could support an explanation for the universe's asymmetry. So far, that pillar has not cracked. Measurements of time-related properties remain consistent with symmetry. Once again, theory survives. And once again, the central mystery remains untouched. This pattern has led some physicists to question whether the search is being framed correctly. Instead of asking which law is broken, perhaps the more relevant question is when. If the asymmetry emerged during a phase transition, then the laws themselves may have changed temporarily, only to settle back into their current form afterward. In that case, modern experiments would see only the aftermath, not the event itself. This line of thinking draws attention to the role of cosmic evolution. The universe is not static. It has undergone multiple transitions, from radiation-dominated to matter-dominated eras, from free quarks to bound nuclei, from ionized plasma to neutral atoms. Each transition reshaped the rules governing interactions. It is conceivable that during one of these transitions, matter and antimatter were treated differently for a brief but decisive interval. Once that interval passed, the asymmetry was locked in, preserved by expansion and cooling. If this is true, then antimatter experiments are not futile, but they are indirect. They serve to constrain models of the early universe, rather than reveal violations directly. Each confirmed symmetry limits how radical those early transitions could have been. Each null result removes speculative mechanisms from consideration. Progress becomes a process of narrowing rather than discovery. There is also the possibility that the explanation lies outside conventional particle physics entirely. Some theories suggest that space-time itself may have played a role. If space-time possessed subtle asymmetries at extremely small scales, they could have biased particle interactions during the universe's infancy. These ideas are highly speculative, but they reflect the growing realization that the matter-antimatter problem may not be solvable within existing frameworks. Antimatter experiments then become tests not just of particles, but of the structure of reality itself. Despite this uncertainty, work continues. Traps are refined. Lasers become more stable. Detectors grow more sensitive. Each improvement tightens the net. The hope is not that antimatter will suddenly misbehave, but that it will eventually fail in a way that cannot be explained away. A shift too large to be blamed on noise. A discrepancy that persists across methods and machines. Something that forces theory to bend. Until then, antimatter remains suspended, literally and conceptually. It hangs between existence and annihilation, between symmetry and imbalance, between what the equations predict and what the universe delivered. Its very presence in the laboratory is a reminder of how close reality came to erasing itself completely. And its continued obedience is a challenge to every attempt to explain why that erasure did not happen. The deeper scientists look, the clearer one fact becomes. The universe did not survive because the laws of physics are generous. It survived despite laws that seem almost perfectly balanced. Somewhere, hidden in the earliest moments of time or the deepest structure of space, that balance was disturbed just enough to allow matter to remain. Antimatter, studied with relentless care, is the closest thing physics has to a witness. And so the interrogation continues, not with force, but with patience, precision, and the growing suspicion that the answer, when it finally appears, will change far more than our understanding of antimatter itself. As this slow narrowing continues, the focus of antimatter research has begun to shift in tone, if not in method. Early on, the hope was that a single experiment might deliver a clean, decisive break from expectation. Something unmistakable. Something that would immediately point to a missing force or a new particle. That hope has faded. In its place is a more sober recognition of how deeply hidden the answer may be. The universe does not seem inclined to reveal its origins easily. It reveals them reluctantly, one decimal place at a time. This has made antimatter an unusual kind of scientific object. It is no longer treated as an exotic substance or a technological curiosity. It is treated as a standard, a reference point. By measuring how closely antimatter matches matter, physicists are testing not just particles, but the consistency of reality itself. Every successful match tightens constraints on theory. Every failure to find a difference is itself meaningful. It tells us that if the universe cheated, it did so in a way that left almost no trace. One consequence of this is a growing interest in experiments that combine multiple symmetries at once. Instead of testing charge symmetry in isolation or parity on its own, researchers are designing measurements that stress the entire structure of physical law simultaneously. These experiments are difficult to conceptualize and even harder to execute, but they reflect a growing suspicion that the asymmetry responsible for our existence is not local. It may not belong to a single interactional particle. It may be distributed across the framework of physics in a way that only becomes visible when many constraints are applied at once. Antihydrogen remains central to this effort because of its simplicity. It is the cleanest possible comparison system. One antiproton, one positron. No nuclear complexity. No hidden structure. When antihydrogen is studied, any deviation cannot be blamed on internal chaos. If a difference appears, it must come from the rules themselves. This is why so much effort has gone into improving the stability and longevity of antihydrogen traps. The longer the atoms can be held, the more carefully they can be interrogated. Time itself becomes a tool, allowing subtle effects to accumulate until they are measurable. Time also introduces another dimension to the problem. The universe does not just distinguish between matter and antimatter. It distinguishes between past and future. This temporal directionality is one of the most mysterious features of reality. On small scales, the laws of physics work just as well backward as forward. But on large scales, time clearly flows in one direction. Entropy increases. Structures form and decay. The universe remembers its past, but not its future. Some physicists have wondered whether the matter-antimatter asymmetry is connected to this arrow of time. If so, antimatter experiments may be probing not just symmetry in space, but symmetry in time itself. Testing this idea is extraordinarily subtle. It requires comparing how systems evolve, not just how they are configured. Matter and antimatter must be prepared in equivalent states and allowed to change, while every external influence is controlled. Any difference in behaviour over time would be profound. It would suggest that the universe treats antimatter as temporally distinct, not just spatially inverted. So far, no such difference has been observed. But the limits of these tests are still far from absolute. This is one of the frontiers where future experiments may yet surprise. Meanwhile, entirely new approaches are being explored. Some involve using antimatter as a probe of gravity in environments far removed from Earth. Others consider the possibility of testing antimatter in space, where interference from terrestrial fields is minimized. These ideas are technologically demanding and remain largely conceptual, but they illustrate how central antimatter has become to foundational physics. It is no longer a niche subject. It sits at the crossroads of cosmology, quantum theory, and gravity. What makes this pursuit particularly difficult is the lack of feedback. In many areas of science, partial success guides the next step. Here, success takes the form of null results. Each improvement in precision that yields agreement with theory provides no obvious direction forward. It simply tells us where the answer is not. Progress becomes a matter of endurance. The motivation comes not from positive findings, but from the sheer weight of the unresolved contradiction. A universe that exists in defiance of its own rules cannot be ignored indefinitely. This tension has begun to influence how physicists think about explanation itself. The assumption that every observed outcome must be tied to a clean local mechanism is being questioned. Perhaps the matter-antimatter imbalance is an emergent phenomenon, arising from the interaction of many factors rather than a single cause. In this view, antimatter experiments are like examining individual bricks while trying to understand the architecture of an entire city. Necessary, but not sufficient. The structure only becomes apparent when the pieces are considered together. Still, there is a reason antimatter remains the focal point. No other comparison is as pure. Dark matter is invisible and difficult to manipulate. Dark energy reveals itself only through cosmic expansion. Antimatter, by contrast, can be created, trapped, and measured directly. It is accessible in a way that few fundamental probes are. If the universe harbors a preference, antimatter is the most likely place for it to leak through. As the experiments press on, the language around antimatter has subtly changed. Researchers speak less about discovery and more about limits, less about surprises and more about exclusions. This does not mean the field is stagnating. On the contrary, it is maturing. It is confronting the possibility that the answer may not be something we can easily recognize. It may not look like a new particle or a new force. It may look like a revision of how we think about beginnings. At this stage, the antimatter question has become inseparable from the question of why the universe has a history at all. A perfectly symmetrical universe would have no narrative. It would annihilate itself and end before it began. The fact that anything persists implies that symmetry was broken, whether gently or violently. Antimatter is the surviving record of that break, frozen into laboratory form long after the event itself has passed. This is why the work at CERN continues with such intensity despite the lack of dramatic breakthroughs. The absence of easy answers has not diminished the importance of the problem. It has elevated it. Every new generation of experiments pushes closer to the limits of what can be known empirically. Each one reduces the space in which speculation can hide. And with every constraint, the universe is forced to confront its own contradiction. There may come a point where antimatter experiments reach a plateau, where further improvements yield diminishing returns. If that happens, the focus may shift again toward new theoretical frameworks or entirely different kinds of observation. But even then, antimatter will have played a critical role. It will have defined the boundaries of possibility. It will have told us with great clarity what the universe is not willing to reveal through simple asymmetry. For now, antimatter remains both obedient and accusatory. It follows the rules with almost insulting precision, while simultaneously exposing the failure of those rules to explain existence itself. That paradox is not a flaw in the research. It is the reason the research matters. As long as matter fills the universe and antimatter does not, the question remains open. And as long as that question remains open, antimatter will continue to be trapped, cooled, measured, and compared, not in the hope of finding chaos, but in the hope of finding the smallest possible deviation from perfection. At this point, the investigation reaches a quiet edge rather than a dramatic conclusion. After decades of work, after machines of extraordinary complexity and measurements of almost absurd precision, antimatter remains stubbornly ordinary. It behaves as though the universe has no memory of the decision that allowed matter to survive. Every comparison reinforces the same unsettling message. The laws of physics as they operate today appear almost perfectly symmetrical, even though their outcome is anything but. This leaves modern physics in an unusual position. The universe itself stands as evidence of asymmetry on the largest possible scale, yet the microscopic laws that govern particles show only the faintest hints of bias. The imbalance that allowed stars, galaxies, and atoms to form is undeniable. The mechanism that produced it remains invisible. Antimatter, studied with patience and restraint, has become both the strongest witness to that event and the most frustratingly silent one. The experiments at CERN were never really about making antimatter in large quantities or harnessing its power. They were about using antimatter as a mirror, polished to the highest possible clarity, and holding it up to reality. In that mirror, physicists hoped to see distortion, a warping of symmetry that would explain why the universe did not erase itself at birth. Instead, the reflection remains almost perfect. And that perfection is the problem. Every improvement in precision sharpens the contradiction. If matter and antimatter are governed by the same rules, then the early universe should have left nothing behind. If the universe exists, then those rules must be incomplete, temporary, or emergent, rather than absolute. The question is no longer whether something is missing from the equations. The question is where that missing piece can hide without revealing itself to experiments that now probe nature with unprecedented sensitivity. One possibility is that the decisive asymmetry existed only briefly. A short-lived phase in the early universe, driven by energies far beyond what can be recreated today, may have eschewed reactions just long enough for matter to gain its tiny advantage. When the universe cooled, the laws settled into their current form, preserving symmetry while locking in an asymmetric outcome. In that scenario, antimatter experiments are not expected to uncover dramatic violations. They are expected to confirm the aftermath, not the cause. Another possibility is that the explanation lies in layers of physics that have yet to be accessed. New particles, new interactions, or subtle properties of space-time itself may have shaped the early universe in ways that leave only indirect traces. If so, antimatter remains a crucial probe, not because it misbehaves, but because it constrains how exotic those explanations can be. Every confirmed symmetry eliminates entire classes of speculative ideas. The space of possibility shrinks, even if the answer itself remains hidden. There is also the uncomfortable idea that the universe may not offer a satisfying causal story at all. The matter-antimatter imbalance may be the result of chance, amplified by cosmic expansion. A tiny fluctuation, statistically rare but not forbidden, could have been frozen into place as the universe cooled. In this view, antimatter experiments will never reveal a broken law, because no law was broken. The universe simply rolled the dice, and this was the outcome. It is an explanation that leaves many physicists uneasy, but unease alone is not a reason to dismiss it. What is clear is that antimatter has reshaped how these questions are approached. It is forced to shift away from dramatic speculation and toward disciplined elimination. It has shown that the absence of anomalies can be as informative as their presence. And it has highlighted the limits of even the most successful theories when confronted with questions of origin rather than behaviour. The work continues not because antimatter is expected to suddenly rebel, but because the contradiction at the heart of existence refuses to disappear. Matter fills the universe. Antimatter does not. The laws governing both appear nearly identical. These facts cannot coexist indefinitely without resolution. Whether that resolution comes from new physics, new perspectives on the early universe, or a fundamental rethink of what constitutes explanation remains unknown. For now, antimatter remains suspended in its magnetic cages, isolated from the world it mirrors so precisely. It does not explode. It does not fall upward. It does not betray an obvious preference. Instead, it quietly reinforces the most unsettling possibility of all, that the universe may have survived not because it was designed to, but because it happened to. And until that possibility is either confirmed or ruled out, antimatter will remain one of the most important tools for understanding why anything exists at all,